R stuff, specific examples. We will post the examples as well. So we will have the code and all of that. And Jake intends to go through a Barry example, so you can kind of work through Barry doesn't use R, but he's going to apply R to a pretty simple example from Barry, right? Mm-hmm. And then second, you're going to do like an R package type thing.
Yeah, some of the basics.
Okay, some of the basics.
Stuff, yeah.
Good. And then are you going to try a stand type thing,
yeah,
basic thing?
I'll try to get into some stand stuff.
Yeah, small.
Yeah.
Jake, are you going to go over hyper-priors here?
No. Yeah.
Oh, I thought you were over there.
Yeah,
Aziz, no. And the reason for it is I'm going to go over hyperpriors after. When we go to linear models that are a little bit more complicated, hyperpriors are not that difficult. You just need to know what the hell they are.
Can we have an example?
Yes.
Afterwards.
Yep.
Thank you. The
Yeah.
examples are very helpful.
Yeah, good. And we're going to try to put as much material online as possible so that, but in order to get the most of this, if you come prepared with your notebook and go through the examples, it'll be useful. And if you're traveling next week, it's no problem, Caroline. You'll be able to download the code and go through it. And I've already seen Spencer teaching in action, and he's very good, and he's patient. So if anybody needs any assistance, but Aziz, you might be called on next week. Some assistance with R. So those people who are proficient in R, like Sam, Jake is going to try to call on your help. Okay. All right. Let the games begin. So we have presentations. It's the same format that we had last month. You may have a single presenter, or everybody can rotate through. Doesn't really matter. You saw that there's a lot of flexibility. I'm not going to hold you to any particular standard. The one thing that I will ask you is, remember we have the rating form. Try to submit your ratings as soon as humanly possible, because some people didn't have a computer or a phone or something like that, and therefore they had to submit the ratings later on. And it's kind of difficult to remember what we observed. So best if you have an opportunity. If you don't have an opportunity to do it on any of your connected devices, just ask somebody to borrow their computer so that we can get these things in. Jake and I, we do look at the data. We do have access to it. And I like to see how the ratings were done. And I also, I don't care so much about individual identifiability, but you need to write in that it is you who's doing the rating so that I can separate student from me and student from Jake and me from Jake. This time around, I have one request as far as rating is concerned. The 0 to 10 scale is not based on a 0 to 100 where a B is 80, a C is, I don't know, less than 8, and an A is a 9 or above. Okay, it's not that. I want to recalibrate you a little bit, where a 0 is an F. That means that there's no redeeming features whatsoever. And a 5 should be about a B. Okay, what I'd like is a little bit more variability in the ratings. I don't want you to be punitive. What I want it to be is constructive. Okay, because I don't base the grades necessarily on this, but I do like to see to what extent you find the presentation persuasive and informative, and does it provide you some insight into the benefits of Bayesian methods over alternative methods. Okay, so I mean, you guys know those are the criteria, and those criteria that I'm asking you to rate, think of it as 0 is an F, and about a 5 or somewhere middle of the scale is about a B. Okay, so it's a truncated scale. Remember, we don't give Fs in graduate school, so it's C, B, and F, and someplace in there. So ideally, with the last time I saw piled up, and they were either 10s or 9s, and I'm sure some of you are probably apologetic and putting an 8, and you're like, I'm really sorry, I just have to put an 8. But now the 8 is going to be a 5, and if you think it's probably not deserving of a B, it's going to be drifting below the 5, okay? So try to use the full scale. Make sense?
Yeah.
All right, Lisa, use the full scale.
Okay,
Got it?
Yep.
0 is a C, let's put a C, okay? 5 is a B, and a 10 is an A-ish, if you want to use letters. Okay, who wants to go first?
We do.
Woo-hoo!
Wow.
There's, all right. Yeah, that was fast.
I had 2 group members staring.
Yeah. So we had somebody. Would you guys, you want to go second? What group number are you? 5. Okay, order.
What's the number are we?
Who are we gonna hook up to the TV?
I think Paul's computer.
Yeah, I have it on.
Yeah, Spencer.
I know, it's always changed.
I don't have Shane Worker.
What?
Yeah, I have it on Google already.
I have
an HDMI input.
Oh, okay.
I wasn't sure our number, so it's never.
You guys figure out
4.
4. Okay.
But we use
5, 4,
2.
2. Excellent.
1.
1. Leaving 3. Oh.
It just count down. It's so close.
I know, but there's a certain lack of randomness to the countdown, so I apologize. All right, everybody on the page that's necessary. Well, let's get it so that everything is all set. Woo-hoo. I don't know how the hell to display it. All right, I got it. All right, group 5. Group 5. Move back here. Oh, you guys waiting? I figured we were waiting on something.
We can try my computer again.
Isn't it built in?
These, just so that you know, these are 5 areas.
TV on.
And no, I'm not checking to see whether you're on Facebook or not.
I don't know why I did that.
Oh, this looks official now, yeah.
It's okay, Paul. You select it.
It looks way more official when it's down. Getting back up.
Just start on that now, Paul, just like.
And we're on group 5.
Seriousness.
Yes, Sam.
Woo woo. That's the rating form.
He's already rated us really poorly.
By the way, I like the incongruency and the thing. Twice. Number 5 variant.
Sorry about this, guys.
Yes, good call.
It makes me happy, actually.
Yeah,
By the way, happy birthday. Didn't even know this in time.
I probably created that thing at 2 o'clock in the morning.
I think you got it.
Yeah, so as we're
I always say it when it's a good one.
as we're pulling this up, I kind of want to introduce our topic a little bit. It's kind of one of the oldest questions, sort of in humanity, really. I think Socrates posed the question.
Oh, God.
Plato, Aristotle. I mean, they really were asking this question.
Oh, God.
Our hot professor's easy.
Which kind of easy?
Yeah.
Well, I guess you'll have to wait and see.
So Nick, are we on?
We're on.
Okay, I'm Mark Go.
All right. So our hot professor's easy, right? And so we're talking about Rate My Professor, obviously. And when we're in Rate My Professor, everybody knows the most important metric in Rate My Professor is the chili pepper. I mean, it's above and beyond the easiness, clarity, helpfulness, and all the would you take again, all those things. Chili pepper is obviously most important. So we're wondering, we do have, studies have shown we do have this bias for beauty. What is beautiful is good. People who are attractive is rated as having higher overall kind of other positive qualities that they may or may not have. So along that same idea, possibly the halo effect. So positive feelings in one area, that being attractiveness, may cause ambiguous or neutral traits to be viewed more positively in a sense, how easy or difficult a class is. So essentially undergrads equal lazy, easy equals good. So our hypothesis is that hot professors will be rated as easier. And we actually have the privilege of having a couple hot professors in here, according to Rate My Professor. Patrick, I believe you have a chili pepper. Jake, you also have, as a
must be blind.
as a formerly hot professor, I have had my chili pepper removed recently. I fear, since my attractiveness has gone down, that my class is becoming more and more difficult. And here's an example, if you will. So here's not paraphrased, this is an exact quote from Rate My Professor. Not gonna lie, I didn't pay attention in class. All because he's kind of beautiful and wears these shirts where you can see his chest and whoa, those skinny jeans. Plus, he's on Tinder. He's super cool and willing to help in this. I wish I'd gone to class more. That might have helped my grade a bit.
So I think we should close the door.
So that sets the stage for kind of what we're thinking.
Okay, so our here's our logic for picking a Bayesian analysis over null hypothesis significance testing, and I'll kind of start with the most obvious point, bullet point number 2. So unlike the null hypothesis significance testing, Bayesian essentially allows us to accept or support a null hypothesis. With you either reject or you fail to reject. You can't really accept any type of hypothesis. Also, ratings are continuously added to Rate My Professor, so in a sense, it's kind of nice to be able to update our beliefs as more ratings come in at the end of the semester, especially if you have a professor who's a dick and maybe failed all of his students. It's kind of interesting information there. And we want to be able to quantify our evidence in favor of our null hypothesis, such as, hot not being easy. Also, it allows for more subjective judgments. So Sam is going to go into detail about the rope and what our 0.5 point rope is.
All right, so when it comes to this very peculiar game of hot or not, in a sense, basically what we decided to do, so on ratemyprofessor.com, easiness is rated on a 5-point scale, 1 being hard, 5 being easy, and that may have changed from what it is now. This was like a previous rating, but basically we're going to be taking our beliefs that hot professors are typically easy and kind of modeling that as our priors. So what we have here at the top, so like on the right hand side to see hot or not hot. So that's basically your binary rating. You have that chili pepper or you don't have that chili pepper. While you have the easiness scale on the bottom right there. So for hot professors, we in accordance with our original beliefs that they have would have an overall higher mean rating than so 3.5 as a mean compared to 2.5. We set the standard deviations as 1, so it'd be fairly, variable enough. It was essentially a good number for us, but yeah, there we go. So we wasn't too confused. So yeah, so then we wanted to actually find our observed data. So what we did is that we went on to ratebyprofessor.com. We pulled 98 ratings that actually were from the professors of. We did try to pull ratings from elsewhere, but it wasn't readily available. So this is real data that we are pulling from the internet. So here is the raw data that's actually overlaid on top of our priors. And so what we observed was, so for hot professors, they had a mean of 2.93. For professors, they had a mean of 2.71. So essentially, we actually do see a slightly higher rating for easiness for hot professors relative to not hot professors. But essentially, it's really fairly close. So does this actually mean anything in terms of our analysis?
All right, so now it's time to combine our sources of information. We have our priors, what we expected to see, and then we have what we observed, what we actually saw. So we're going to combine them into a posterior. So we use the best package in R to do this. And like Caroline mentioned, we use a 0.5 rope. So what that means is if we see the difference between the two groups to be anything than less than 0.5, essentially we're going to say it might as well have been 0. So essentially it needs to be greater than 0.5 for us to interpret the difference as being meaningful. We're also going to use the rope to make a decision about the two hypotheses. So we have hypothesis 0, which is the null essentially, that there is no difference in easiness between hot and not hot professors. And then we have the different hypothesis, the alternative, so to speak, which is hot professors are easier. And so we're going to accept the null if 95% of our 95% HDI is inside the rope. And we'll accept the alternative if 95% of it is outside the rope. So with the rope, it's basically a way for us to figure out how confident we are that an area is inside of another area that might as well be 0. So what we observed is that hot professors are not easier. So what we have here on the left is a histogram of differences between the two groups, hot and not hot. And what we can see is that for the most part, the two groups are equivalent. So these values were generated from a random walk procedure. Basically, a random value from each distribution was chosen, and then they were subtracted. That value was plotted here, and that was repeated a bunch of times. So we have a reliable estimate around 0. The mean was actually 0.2-ish, but remember, we had our rope set at 0.5. So anything that's within negative 0.5 and 0.5, we're going to say, it's basically 0. The graph on the right essentially shows that as you increase your radius of the rope, so as you step away from 0, you can see that the area of the posteriors increases. So basically what we have is 95.2% of the 95% HDI inside of the area that we said might as well be 0. So basically 95% confident that the difference is essentially 0. So hot professors are not easier.
So in conclusion, as Sam has just said, hot professors are not easier, just some limitations about the real data that we were messing around with. We didn't have equal numbers of ratings for hot versus not hot. So maybe Harvard professors are just ugly. And then we did have to kind of force our scale as a binary categorical variable. So hot versus hot, not hot. So something, beauty is in the eye of the beholder, blah, blah, blah. It's subjective, so maybe beauty and hotness can be analysis and whatnot. And I think that wraps it up. Any questions?
What if only 50% of your 95% HDI was within your group? What would you have done then? Because not 95 was outside of it and not 95 was inside of it. What would you do in that in between?
I guess we wouldn't really have strong evidence for either hypothesis then, yeah. Good question.
Why did you set the rope between at 0.5?
So, oh,
Just us.
so
Remember, the rope is really subjective. You can make it whatever you want.
Yeah, but I mean, I can say that it's
And
Maybe
also
between
our,
-1 and 1.
our scale is also kind of small, so it's 1 to 5, and so we didn't want to pick 2 because then it's half the scale. And we didn't want to make it super tiny because then we would be kind of stuck with small.
Yeah, I mean, you could think about when you're comparing your scores with a friend. I mean, if you beat them by like 0.2, you might be like, yeah, I'm so much better than you. But they'll probably say something like, whatever, it doesn't count. But if you beat them by a solid point, there's no denying it, you know? But yeah, subjective.
Good job, guys. All right, group 4. Come on down.
We just got something. Just there.
Oh, that's not promising.
Sometimes you're at home. It might be the resolution.
Ah,
Aha.
Jake, do you have an easy or hard rating?
Pretty easy.
it must have been those skinny jeans.
In that chest.
Whoa.
Ready? All right, group 4, here we go.
Okay. I am the spokesperson for group 4. We decided that we were going to look at whether the recalled and replaced Galaxy S7s actually catch fire and explode less frequently than they did before the recall. So our grandmother, well, we're not related, my grandmother would like to buy a Galaxy S7, but I am concerned about this because they've been exploding. I can't have a phone exploding in her purse, that won't do. So I would like to know if the recall has actually fixed the phones, because I've heard some rumors that even the replacement phones are exploding. I'm just generally not at ease about this plan of hers to buy this phone. So I decided to do a Bayesian analysis because all frequentist statistics can really tell us in terms of accepting the null is that we can't say that the new phones don't explode just as often as the old ones. And I would like something more definitive than that. I need to know for sure, are these phones exploding at the same rate or are they not? So our null hypothesis is that there is no difference in the probability of explosion. The new phones will catch fire in your pocket just as often as the old phones would. And the experimental hypothesis is that the new phones are far less likely to explode than the old phones. Ideally, that they will not explode at all. So we expect this recall to have been either a total success or a total failure. They either took the combustible material out of the phone battery or they failed to. The phone is either going to explode or it's not going to explode. Allowing for error in our measurements, we decide that anything between negative 0.15 and positive 0.15 is going to be, we're going to count that as the same, as no difference between the pre and post recall phones. We want to have a little bit of a buffer room because we don't want to be wrong and have grandma's purse explode while she's in like a Hallmark store or something, or anywhere. We called 350 people who had the phones before the recall, and 161 of those people said that their phones exploded. We called them on their landlines, I guess. So this curve then represents our estimation of what the population of old phone probability of explosion is. We then called a different 350 people who had the new phones, and actually 175 of those people said that their phones exploded. So this is our estimate of what the population explosion probability is for the post-recall phones. So again, we had decided that negative 0.15 to positive 0.15 is going to be the same as 0. As it turns out, 99% of our best guesses of the difference between the pre and post recall phones are the same as 0, and so therefore there's a 99% chance that they did not fix the old phones. So nice try, Samsung, you have failed. So in conclusion, we can say with confidence that the recall was ineffective. There's no credible difference in the mean probability of phone explosions between the pre and post recall phones, and therefore a null hypothesis was supported. And we will be buying my grandmother an iPhone 7 for Christmas. Okay, that's it. Any questions? All right, well, hopefully that means I did a good job of trying to keep it simple.
You did a great job. What does a rope represent? And you don't necessarily have to answer this. Somebody on your team can answer it as well. But what does it represent?
Do one of you guys want to?
So I like the example you gave with Google, because you're looking at, we don't want any deaths, but what deaths do we say are not the responsibility of a Google product? And so we say, this is the population deaths that occur, and so we're not going to count that as being the fault of Google. And so in this example, negative 0.15, 0.15 is, these are just phones that they die not because of some sort of systemic problem, but because somebody did something stupid with it, where they left it next to something that was too hot, or it was in the sun, or it was left in the car, or something like that.
Okay, yeah.
I'm going to give a different answer.
Yeah, good.
Sorry, Kevin. So we're saying that the rope is our subjective idea of what we're deciding is the same as 0. Like, so phones exploding is like a fairly big deal. If I had a phone in my pocket and it exploded, I would be very upset about that and maybe have to go to the ER possibly. So I don't want, it's like a buffer, allowing for error and allowing for just your subjective idea of like how precise you want to be. It's unlikely that you're ever going to get an exact point estimate of like, this is exactly 0. So you're creating a buffer of will allow it to vary this much.
Right. Both of your answers are good.
Good job, Kevin.
Yeah, they're both good. And you have another different.
Just like a frequentist model, they use 95% as the area to accept the hypothesis. So that kind of 9% also arbitrary. So in Bayesian statistics, our rope is also not an arbitrary acceptable area. That's equivalent to frequentist model. So
Right. So all of those are great explanations of what rope is, right? And the purpose of rope is that the region of proximal equivalence gives us a metric by which we can evaluate our outcomes. Now I turn to a way more specific question: is what does 0.15 represent? How would you explain 0.15 to somebody besides rope? Let me give you some examples. Is that 15% of the phones that were replaced exploded? Is that what?
So that is the difference in the mean probability of phones exploding. We're saying that if the new phones are between 15% less likely and 15% more likely to explode, we're saying that that's the same thing as them being 0% more or less likely to explode.
Excellent. So you see how it's, you guys are giving me the technical explanation for rope. Remember that your audience members oftentimes have no idea about any of this stuff. So you have to be able to communicate it. If you stand in front of a bunch of businessmen and explain rope to them, they're going to be ordering on their Amazon online thing, trying to figure out what to shop for next.
But it won't be a Galaxy S7.
But it probably won't be a Galaxy S. That might be an iPhone 7 if they exist. So that's good. I want you guys to see that that's a distinction between kind of the technical understanding, which I think you guys have. You definitely know this. Try to move it down so that it's easier to communicate to, ignoramuses like me. All right. Good job. Excellent. Yeah. I know. Group 2?
Spencer kills Kevin. Yeah.
Just a bag of
Bags of headphones.
No, my
Yeah.
was.
Two.
I'm sorry.
It's either one. That's pretty good.
2.
Two.
Excellent. Ready?
Yeah.
Marcus, go.
All right. So with election season being in full swing, politics are kind of on our minds, and it kind of has us wondering, kind of pose the question, does our opinion actually matter? We have opinions left and right, and we have to see on our social media streams, and everybody wants to talk about it, but does that actually influence the policies that are being passed and the people who are being put in office? So just to kind of set the stage a little bit, so we all hear about like the elite, America's elite, and how they have all the power. But it is kind of a fact that the top 10% of citizens, referring to the top 10% socioeconomic status, do own about 75% of the country's wealth. And that actually causes gain in power because those people can afford lobbyists. And then it causes those policies to be passed to benefit their business goals. And it's pretty corrupt. So we wanted to ask the question, does the average citizen, so not the elite, but the average citizen's opinion actually alter policy outcomes? So our belief is that it doesn't. So the variable is going to be opinion. So either yes or no, it's a binary variable. And so either yes, I am in favor of this policy as an average citizen, or no, I'm not in favor of this policy as an average citizen. And the outcome is going to be the policy outcome. So does the policy pass or does it fail? So if the null is in fact true, then public opinion has no effect on policy outcomes.
So we found, done at Princeton University, where they were looking at the question, does the government represent the people? They took almost 1,800 instances where a survey was collecting data on public policy opinions as well as income level between the years 1981 and 2002. So the ideal, shown by the graph here, would be that if 100% of the people supported an idea of the time, it would become a law or a person would become in office or something. If 0% of the population supported the idea, 0% likelihood that it would become a law. Unfortunately, with the data that they collected, that's not what they found. Here, the purple line represents the bottom 90%, and it looks like no matter how many people support an opinion, it's about 30% of the time or likelihood that it will pass. That's different with the elite. You can see that the yellow line is much closer to the ideal representation. Unfortunately, because that's really good. So our question, like Keiko said earlier, is how much is public policy impacted by the opinions of the American people? Considering the bottom 90% specifically, does the government represent us? We want to see if data from 2016 will yield different results than the data from the 22 years collected in the Princeton University study. Okay, so the data we actually used for our project consisted of 2 binomial variables. So we polled public opinion over 1,000 bills that were posed to Congress and passed this year, passed or failed this year, voted on. So what our data actually consists of is the popular opinion, and that would be for any instance of a bill. Was the majority of the population for or against? So just yes or no, did it pass the 50% or not? And then we also have those instances where it passed or failed in Congress. So since we had 2 binomial variables, what made sense to do was the logistic regression. So that's our idyllic approach, would be this sort of red line that you'd have a lot of effect of public opinion on the actual policies that were passed. So our x-axis represents our independent variable, which is just the public opinion, and the y-axis represents the likelihood that it'll pass or not. So we really wanted to see if there was any impact at all. So our row parameters that, in this case, we thought before doing any analysis made sense, is there any sort of a slope? Is there any sort of relationship between them, plus or minus 0.5?
So just to make the point here once more. So what we expect, if the policies are actually influenced by the population, we'd expect a line like this, right? So if the population wants a law, then it will be passed. If the population does not want a law, it won't be passed. So our hypothesis is that that's not the case, right? The Princeton study did not find it. So it should be like a line like this, like in the Princeton study. And we chose a row to be between minus 0.5 and plus 0.5, so that there are some variance of because if it's 0.5, it's clearly close to 0, so there's nearly no influence at all. Parameter we're looking at is actually the slope of our logit fit, so which is here it's 6 and here it's 0.5, here it's minus 0.5. So that's what we're looking at in our analysis. Yeah, and that's what we actually found. So we showed you the data, and well, that's our actual data, and well, it falls right between our right in the middle of our slope of our row parameters. So face validity would say, well, this fit looks like there is not really any impact of the population's opinion. The more elaborate answer is, well, we looked at MCMC samples of this parameter. So like with the difference score in Samstock, here it's the slope parameter. So we expected it to be 0, so flat line. So that's why our parameters are centered around 0. And then we included our sample in the MCMC process. And then we ended up with a posterior peaking at around 0.1, which is pretty close to 0. What we concluded is that, well, population's opinion does not have any influence on policy making because our highest density interval was completely zero. So yeah, just to sum it up, yeah, that's what we found, right? If you remember the graph, we found 0 influence, while the ideal representation would be slope equals 1.
All right, so why we picked the Bayesian method, we wanted to look at the probability that the bill would be passed, given popular opinion at the bottom 90%. So the Bayesian method will allow us to take into account past instances where the popular vote was collected for previous bills, and allow us to look at the likelihood that our current bill would be passed. And yeah, so basically the Bayesian approach would allow us to take into account prior data. So conclusion. So because our sample slope and HDI both fall within the rope, we accept the null hypothesis. So basically the probability of 90%, the bottom 90% affecting the passing of the bill is very low.
Any questions?
How did you calculate the slope? So I know you had binary data and a binary outcome. So how do you get a slope from that?
So it's the logistic fit. So we just fitted a logistic model in that.
Is it some other package?
So there is a best logic thing. So there's an MCMC package only for logistic regression.
So your input was probability, not ones and zeros, right? Is that what it is? Probability being a one.
So it's our
Or
sample.
passing?
It's our data, right? It's our binary data, zeros and ones.
Yeah, it's ones and zeros. And so how do you, back to the question that I asked the previous group, what is the rope representing? The metric itself, like what would be a 0.5?
So for us, I think the rope just represents what we consider as an effect that is small enough to say it's no
So
effect.
that's the theoretical side of it, but what is 0.5 in a logistic regression?
I mean, for us, it's just this relationship, right?
Yeah, exactly. And so what does that slope represent? Do you guys know? If you don't know, if you say, geez, I have no idea what the hell that slope means.
Should be the effective X on Y.
Yeah, and that typically is for like bivariate OLS regression with normal distributions for the residuals, but not for logistic regression. Logistic regression is a little weird. So the 0.5 is actually an odds ratio. Yeah, and it's okay, but again, when you use the term rope and you say that it's 0.5 to minus 0.5, that's good. And you guys somehow or another, you chose a really good one because by not knowing that it was an odds ratio, you chose one that's flat, relatively flat. But what that's telling you is just think about that the odds ratio is really pretty minimal in terms of what the difference is between favoring one group versus another, because your predictor is binary and your outcome is binary, right? So that 0.5 isn't a normal B and it's not a beta, but it's an odds ratio. And it's telling you that there's not a lot of evidence. But if you looked at that really steep line, that ogive with a really steep, that odds ratio is 6, right? That's what you said.
Yes.
Yeah, so the bigger that odds ratio is, the steeper. Now, and that's a positive effect. And if it's a negative effect, it just has a negative slope. Think about this, and this is just kind of a heads up for everybody that when you're presenting these ideas, make sure you look at the numbers and you know what each one of those means. You know, that you can explain to a person who's a voter what that 0.5 means. That it is in logistic regression an odds ratio, but in, say, OLS regression, it would be a B if it's unstandardized or a beta if it's standardized. Or in the case of the 0.15 for the cell phone blowing up, it was the probability that the difference between the recalled and refurbished or new cell phone versus the old one, that 0.5 is 15%. So this 0.5 or that 0.15 is 15%. This 0.5 is a difference in odds ratios. Okay, sound good?
That was a good teaching moment.
Yeah, no, exactly. And that's why I like these. This is not punitive. This is just an opportunity to, because the next presentation, I want to make sure that nobody has numbers that you look at and go, geez, I don't know where the hell those numbers came from.
The next
Okay.
presentation for the third project.
Third
right?
project.
Okay.
Yeah, no. This is, yeah.
Better
No,
get your shit together.
the next group is going to be held accountable for this.
The appropriate changes.
Just check.
Well, sitting back here is kind of nice because I get to see Spencer sitting there probably changing the slide now.
He's sweating.
And I see it shared with 3 other people, so they're probably looking at it. He asked that question, let's put this number in. No, it's not for presentation number 2. It's for the third presentation for all of the groups, okay? I don't want you guys to benefit just by going last in the order, but that was really good. And let me just tell you, it's not just terms, but it's also in relative terms, and this is what I was interested in keeping the groups together, is you guys took the feedback the first time around and you turned it around to a way easier presentation. It was great. This was fantastic. So, I mean, I was a little ebullient in my praise. It was like, this is great. So fantastic, great turnaround, very simple. Okay. Sorry I didn't give the other groups feedback. You guys, every group's been great so far.
I'm sure there'll be some feedback from ours.
I didn't say
I have no idea.
You can blame me, I guess. It's all right.
Yeah.
It's 2 ways.
Nope, doesn't like it. No?
You could also just try plugging the HDMI in. Instead of
That's
using
a good
oh,
idea.
no, there it is.
That's it. Oh, that's our presentation.
just the group Jeff side.
What?
Nope.
Oh. This is awesome.
Okay, we're not getting presenter notes. That's not happening.
Yeah, I don't think people can do that.
Just wing it, dude.
Look at the notes on the other computer.
Spencer, it's okay, we have time, just take your time.
Kinda.
Mostly good.
Good enough.
That's for sure.
Yeah. All right. Cool.
All right, Jose, you're not losing your kneecaps on this one.
No, not this one.
Okay.
Well, I did receive a very interesting call this weekend. So I got a phone call, and lo and behold, it was Bernie Sanders. Look at that.
There's no phone call.
So he had heard about my mishap with my kneecaps, just barely skating away, and not knowing who else to turn to, he asked me if we could do a little analysis for him. Apparently, after losing the Democratic nomination, he started moonlighting as a factory worker in a Donald Trump bobblehead factory. And having just turned 75, I believe, he was, how do I put this? He was given an early retirement package. He didn't want to leave, but they kind of pushed him out the door. And him, along with 2 other individuals who are age 75, were being pushed out the door by their manager, Hillary, someone else who apparently has been moonlighting. Maybe that's where some of the email crossover happened. But the older workers, Bernie included, were protesting against this. And they're saying that their performance is not a function of age, and the company should not be pushing out us workers at age 75. Bernie needs that money. He's a little sore. He needs some help. So for our hypotheses, to help him out, basically, Bernie wants to say that there is no relationship between age and performance. In his words exactly, he says, we are just as productive as these young whippersnappers, and there's no reason we shouldn't keep our jobs.
It's not our JFK.
If true, Bernie and the other 2 individuals who are being wrongly fired, and they should actually keep their jobs. However, for the factory's hypothesis, like, no, there's definitely always a negative correlation between age and job performance. And even if these old geezers are okay to still work, old people overall get worse at their job around age 75. Thank you. From Hillary.
Your Hillary
They do not, unfortunately. If that's true, then Bernal should be fine because they're lowering production of the factory, right? So our variables are age and years and performance, and that's bobbleheads made per week. I got some basic data from both the factory and from Bernie, and apparently overall performance for the previous fiscal year was 1,000 bobbleheads per day per worker that was covered, and with a standard deviation of about 62 bobbleheads per day per worker. And in the current sample, we've only had 3 workers though who are at age 75 who are getting the boot, and so we are comparing those 3 individuals to the roughly 200 workers who are under the age of 75 who are also working in the factory.
So since we only have 3 workers in the older category, we decided to run an MCMC to resample that data so we can make a reasonable conclusion from our analyses. In addition, we ran a t-test. Since we're comparing mean performances, we figured a t-test would be best. It's just a really simple way to compare differences in means. For our analysis outcomes, we looked at the HDI, which is basically, as you've heard several times before, where most of our data falls once we run the analyses. It kind of excludes outliers. It looks at your most central data. And then we also implemented the region of practical equivalence, or ROPE, which is kind of like a confidence interval where you want if you're trying to support the null as we are, you want your HDI to fall within the ROPE. Yeah, and if a way to interpret it is if your HDI does fall within your ROPE, you can basically say that you're supporting your null hypothesis, or that the data is practically equivalent, or there's no real difference between means.
So just to kind of reiterate the rationale for why we use the different parts of our analysis. For the MCMC, we selected that because we had a small sample of older workers. We did the t-test for a difference between means because we had 2 groups of data. We had the younger group, and then we had Bernie and his small cohort of older people. We chose a ROPE because it provides a good metric for us to measure and demonstrate that either there is support or there's not support for a null hypothesis. And then our HDI is going to represent how different the production numbers are than younger workers because it's going to tell us where the largest number of those differences fall. So to set our priors, we used the data that Jose mentioned, which was data from the previous year of production that told us that last year's average bobbleheads per, I think this was per week, was 1,000 per week. So we set a normal distribution of priors using that 1,000 as the mean.
When we examined the means descriptively, they were very close to each other. So being the frequentist that I am, I looked at my group and I told them, listen, this Bayesian nonsense, open the hood, close the hood, I don't like that stuff. So let's just run a t-test and let's see what happens and we'll just go from there. So when we ran the t-test, we got a t-statistic of the p-value was extremely small. So we rejected the null hypothesis, which is that the means were so they convinced me, and we looked at the distribution of the mean difference between the 2 samples, and we get a mean difference of -2.4. 69.6% of the sample was less than the average, and about 30% was performed better than the average.
At the end of the day, we aren't frequentists, we're Bayesians, so therefore we use the ROPE. The factory went ahead and set a ROPE of plus or minus 10 bobbleheads per day on either side of that mean. Now, 10 may sound like a lot, but when you're talking about around 1,000 bobbleheads produced a week, that's only 1% of actual output. So that's actually a very small difference. When we ran our HDI, that falls entirely within the rope. On the lower end, 9.94, and on the upper end, 5.85. So if we're using a rope, we can very reasonably conclude that there is no difference between these groups. So therefore, using Bayesian as opposed to frequentist, that's the null. So to wrap it up, we would have to conclude, using this method, that Bernie Sanders was unjustly fired for being too old to work, as age in this particular job is likely unrelated to performance. Bayesian, we can't say for absolute certainty that age is unrelated to performance, but given this data, we can reasonably accept the null.
Also, none of this reflects our political opinions.
I'm trying to bring in race. They can be useful.
Do you need to see a specific slide?
Questions?
Oh, right, now I remember. So how do you explain and justify the difference in your frequentist results and your Bayesian results since you displayed them?
Well,
Okay.
since we used an MCMC, our sample became so large that basically our power became like, it was like p-hacking, right? Like, so any difference would have been statistically significant.
Yep.
So since the mean or the difference in means was actually like subjectively really small, but statistically significant, we decided to just throw out the t-test.
So it was stupid overpowered.
Yeah,
Yes.
the problem with doing the t-test in this scenario is that if we ran it with just the sample that we had, we would have 3 individuals and then looking compared to 200.
Yeah.
Yeah, and even if we pick 3 randomly from that sample size of 3 is probably not the best idea to look at. The fact we probably argued that the power is not enough. So we ran the MCMC, and that increased then our sample size to a point though that it was stupid overpowered, and we got that crazy significant result. And so we flipped to Bayesian, which was a more accurate representation.
So how do you describe the advantages of Bayesian if you took the t-test to the factory floor and said it's significant at 2 bobbleheads a day, and they said, well, we only care about 10, so we're not going to pay attention to that? Would the outcomes be the same?
Say that again?
What do you mean? So like if you took the t-test to the factory and said it's significant, both people make 2 fewer a day,
Okay.
and then they went, well, we only care about 10, so it doesn't matter to us. Would that be the same outcome as the Bayesian?
At the end of the day, the effect of it would be the same. If they had whatever, I guess the frequentist version of their rope would be confidence interval, thank you. And yeah, the outcome at the end of the day would be the same.
However, in this case with the factory, I'm sure that the managers and the owners of the factory would argue for any reason possible for firing people. So even if you say, oh, it's a significant difference from the t-test, even though if it's only 2, that's still there. Hey, it's different. Get them out of here. Versus, say, now if it was flipped the other way, and we were trying to argue that they were keep their jobs for a difference of 2, and they were like, oh, we only care about 10, then maybe it wouldn't matter as much. But in this case, I think they would use an excuse. So Bayesian is still a better reason.
That's significant, but the effect size is like minuscule.
Yeah, it doesn't matter to them. I'm sure they would say.
And just to highlight that, there's been a big push in statistics to move away from statistical significance to clinical or meaningful differences. And many years ago, Truax wrote a paper about clinical significance, but it wasn't necessarily about clinical, it was about practical significance. And I think that Sam's question is really one to for all of us to think about, is at what point are we really gaining much? And from a Bayesian perspective, if we could just hold on to the null hypothesis significance testing and abandon the p-value necessarily if it's overpowered, and just say, I don't care if it's significant or not. I care if it's practically meaningful. So there's, I think, and that's the reason why I'm kind of harping on rope, is that I want to make sure everybody's using rope, but they understand what those numbers mean, so that then you can talk to somebody who has no idea about statistics. As I started the class out, the advantage of Bayesian statistics is we should be able to talk to people who know nothing about statistics, know a little bit about probability, but talk to them in the metric that they understand. This presentation was excellent. It was excellent because it provided that contrast between the frequentist and the Bayesian. The questions I thought were really good as well, because they pushed you to start thinking about, well, at what point would we abandon the null hypothesis significance testing, and what is the practical significance? And I like the way you framed where you got the rope and and you expressed it in a metric that was understandable. And I hope it wasn't because I was asking those questions.
It was.
It was.
There's a clear effect.
Yeah, there's a serial effect. Yeah. Was that?
We decided on it last night, but then we wanted to emphasize it, especially after hearing.
Yeah, we decided on that 1% parameter, previously, which was pretty stringent.
Sure.
Some credit goes to the groups before us.
Yeah, exactly. Acknowledge that, because that happens in business, by the way. You get a series of presentations, and all of a sudden people will leverage off of the previous presenters and say, you know what, so and so made this point, and now I'm gonna tell them that they're wrong. All right, good job. Group 3. So, but the rope is not necessarily easy. It's an application. Proximal. Because it's a proximity. Sorry, Shane.
No, ready when you are.
All right, Marcus.
All right. So as a video gamer, I get a little triggered when I hear these politicians and lawmakers try to blame video games for these increases in crimes or gun-related crimes, things like that. And video games, they are an easy target. They've become quite graphically violent and pretty ubiquitous in the pop culture. But the thing is, we heard these same arguments against the media type a few decades ago, where people were trying to blame television for increases in crimes. But in 2016, you don't hear many people trying to blame TV for incidences like the Sandy Hook shooting or events like that. So if these politicians have resigned to the fact that they can't blame TV for causing mass murders, then they should stop trying to blame video games too, and maybe focus their efforts on more beneficial changes. So that's the goal of this presentation. We want to show that the aggression levels between video gamers and TV watchers is not different whatsoever. So how are we going to do this? Well, we're going to expose participants to 10 hours of 2 different types of media. So we're going to have them either play 10 hours of one of the most popular violent video games, Call of Duty, or we'll have them watch one of the most popular violent TV shows, Game of Thrones. And then before or after their exposure, we want to have them fill out an aggression questionnaire. So the metric we're interested in is the change in aggression levels from before to after the media exposure. From 0 to 150, higher scores indicating higher levels of aggression. And the standard error on the measure itself is ±5. So our hypotheses, the null would be that there's no difference in the change in aggression between TV watchers and video gamers. And then the alternative would be that there is some change in aggression levels after watching TV or video games. An important note here is why we wanted to use a Bayesian analysis. Well, there is a small body of literature that would argue video games are more immersive. TV is a much more passive experience. So video games may have more of an effect on your mood. So violent video games may increase violent tendencies. So our argument we wanted to make is even if these paltry few research papers are showing this effect and making that argument, we're still going to show through our data and our analysis that there's no difference in aggression levels between these two media types of exposure. And Bayesian allows us to put this assumption into our analysis, whereas a frequentist would make us assume that the null and the likelihood of observing the null or the alternative is equally probable. With Bayesian, we're allowed to take those assumptions from that small body of literature and shift the probability of observing that null away from the null and towards the alternative. So what does that actually look like in the priors that we're using? On the left, there's the Game of Thrones exposure. It's centered around 0, a little tough to see. But so that would indicate not much of a change in aggression after watching Game of Thrones. Whereas that literature would say maybe Call of Duty is increasing your aggression levels a little bit with its violence. So that distribution shifted away from the 0, that no change, and towards positive increases in aggression. And then our evidence that we actually collected, the data we collected, here's the 2 distributions as well. The Game of Thrones distribution's little above 0, but very close to 0, so not much of a change in aggression. And then the Call of Duty, very close to 0 as well, not much of a difference between the 2. And then after sampling from these distributions over and over again, we got an estimate of the population. And this is what's represented here, and using our rope analysis. So those are the 2 population estimates overlaid on top of each other, with their means as the vertical bars. And then the rope we chose was equivalent to the standard error of the metric itself. So that's why we used that. And you can see the means of both those distributions falls well within that rope that we chose, just the variability in using the measure itself. So practically equivalent distributions between the 2. This is just another graphical representation of those population estimates with the high density intervals in place. And you can see that those fall well within that ±5 standard, that ±5 rope range we chose as well. And then just one final graph here, just to again solidify these facts that the distributions really aren't different between these 2 groups. This is both conditions on the same graph. So this is just the difference between the 2 conditions after all of those hundreds of thousands of samples, what the mean difference looked like. And you can see, again, centered around 0, really close to no difference between these 2 groups whatsoever. Watching TV or playing video games really doesn't have an effect on increasing or decreasing your aggression levels whatsoever. So these politicians, stop trying to blame video games, try to tackle this problem of violence and increases in crimes from a different, more productive angle. Any questions?
Why are you comparing 2 groups between watching and playing instead of watching and not watching, or playing with not watching?
Really, because we just wanted to show the difference between those 2 groups. We didn't want to say, we didn't want to really analyze what no media exposure looked like. We just wanted to analyze the difference between these 2 and say, hey, if you stop blaming TV watching on these violent crimes, and there's no difference between these 2, then why are you trying to blame this equivalent type of media?
For that plus, and in America, media exposure is ubiquitous. Everyone either gets some kind of exposure to TV or video games. It's pretty consistent across the board that people do get media exposure no matter what. So you have to ban aggression across all media or stop picking on video games.
So watching and playing are still belong to, so we can still consider they are both belong one predictor.
I mean, we would argue that it's 2 different predictors, 2 different types of media exposure. They are both still media, but it's 2 different types of media. One is being blamed for an effect, while the other isn't being blamed for an effect. We wanted to show that there is no difference between these 2, so you can't blame either. Does that maybe help? Okay. What's up, Sam?
So using a standard error as the rope, is that kind of like graphing it and eyeballing the error bars?
No, so we would say that standard error that we collected was from a meta-analysis of this questionnaire that we used, and over all these iterations, that just the variability of applying this metric itself, there's this ±5 points on the scale that may vary. Yeah, that's what that is. Yeah, so our rope is just the variability of the measure, really. Anything else?
It's actually the the reliability of the measure expressed in the metric that comes out.
Okay.
So you did a good job. It's just 5 data points, plus or minus 5 data points. And then typically we would use 2 standard errors of measurement to provide us with kind of a 95% confidence interval around any estimate. So in other words, that if you got the range was 0 to 150, right? So if you got a score of say 100, that the 100 could actually be 90 to 110 in true score.
Gotcha, yeah.
And that's just noise around any individual estimate.
Yeah.
But that was a good justification. Is you just have to say we chose the standard error, but you only chose one,
Which is more stringent.
which is way more stringent. And so a lot of people would say, well, why one, man? That's really narrow. But you showed no effect. So part of what you could say is not only did we just take one standard error, which is way more stringent, but we applied that in light of the fact that we were searching for the null. See, if I were looking for, it's kind of like doing a one-tailed test when you're trying to reject the null. People are like, you're just making it easier to get over that hurdle. But you made it more difficult using a narrower row to accept the null, right? And that's what I'm talking about in terms of understanding what the metric is and really communicating it to your audience, that you really want to make sure that your audience appreciates the fact that you've chosen something that's either stringent or relaxed based upon what your aims are. Yeah. Okay, good job. Excellent. Excellent. All right. I hope everybody voted and submitted your ratings. Jake and I will analyze the data at some point and give you guys feedback. We'll wrap up in 2-3 minutes here, but I just want to thank everybody for doing a great job. This was another excellent round of presentations, and I hope you're finding that doing these group projects is worthwhile and informative. That I want it to be educational. I don't want it to be a trail of tears, because I would prefer that you have an interest in learning these skills further, and that it dangles a little bit of what's available for you right now, and that you learn how to be a long-time learner in this. The tools will change, guaranteed. They will change rapidly. In fact, I was just on a stats.org panel where we were discussing the changes in STAN, and Gelman is likely to entirely new syntax within the next 12 months. So whatever you learn today won't necessarily carry over. I mean, it will somewhat. But what they're trying to do is incorporate STAN into an interface in RStudio. So just to give you a heads up that there may be a little bit easier interface and an easier way to run Bayesian analysis. Okay, great presentations. Really appreciate everybody making the effort. I'm happy that everybody's also attentive and rating. Next week, remember, Jake is going to come here and give you specific examples. Please come if you're at all disposed to learning more. But Jake is going to walk you through examples, starting with, as I mentioned to everybody, starting with Barry code, R applied to Barry's book, and then a package, and then a little bit of STAN stuff. We're not going to do hyperpriors yet. And the reason why hyperpriors are relevant is if Shane decided not to do a between subjects design, like Peng was asking, why these two groups? Well, what happens if he did a within subject design? Well, within subject design changes, because think about this. Think about a within subject t-test, right? So you have a test, retest, where you're doing, and you want to compare the results, but instead of doing a t-test, between groups, you do a t-test within group, change your expectancy for that dependency, that within subject dependency, right? We would use a hyperprior for that. I know that several of you have been asking about hyperpriors, and I'm going to slowly bleed in the information so that you understand that hyperpriors are just a way in which we model that dependency, okay? In the easiest way is going from an independent t-test to a dependent t-test, okay? And then later, we'll do all sorts of things with linear mixed effects models. Okay, so next week, big week. The last thing I want to ask is, I'm going to send out a form, another form shortly. Actually, I'm not going to do it as a form. Please email me directly if you think that it would be beneficial to change up the groups. No? Okay. Well, no, that's, so if you like the group and it takes a while to kind of relationship and move forward about that, great, great. And I know I read everybody here. I like to see what your feedback is, but if you like your group and you want to stay, great. And if you say we really need to change up the groups, I would consider that as well. Okay? I just want to know what your guys' thoughts are. I think it's helpful for you to find a working group, because after the semester, you will have another working group, but it won't be necessarily the same people. Okay? All right. I'm off to the Bahamas.
Don't look too happy about it.
I will have email until Sunday, so if you need anything from me, please feel free to email.
No way!
Yeah, just gonna ask him.